The Science Museum, home to many of man's greatest engineering achievements. The Model T, the world's first mechanical computer. The Spitfire, the turbofan engine. An exhibition of what the human race has truly achieved. But this year, in 2014, something new will join their ranks. The Group 6 wind turbine.
This is Taming the Wind, the Group 6 webcast. When we came to actually designing the turbo blade, we wanted a design that was very powerful, very capable, but also remarkably simple. There were two critical factors that we wanted to examine. First was the aerodynamic efficiency of the turbine blades, and secondly the structural rigidity. For that reason we decided to come up with two completely different aerofoil sections to represent different parts of our blade. We wanted to have a very aerodynamically efficient, so therefore a high lift-to-drag ratio blade on the outer part of the wing, and a much thicker aerofoil section as we got closer to the root. We use a Q-blade optimization software in order to find the best chord length and angle of attack at various points of our blade. And the good thing was this software also correlated quite well with the book Aerodynamics of Wind Turbines that we were suggested to use by the librarian, and this came out as a very good correlation, so we decided that was probably the best way to go. What makes our wind turbines so unique is the inherently low drag, especially at the root section compared to other groups. This was mainly due to our idea to make the root a lot shallower in terms of angle of attack than a lot of groups. We believe that our wind turbine would have no problems self-starting, and so sort of penalising ourselves by having a large angle of attack was not beneficial, especially when the wind turbine got up to speed. So we decided to use the SG6042 section for the outer part of the wing, as it has a very, very high lift-to-drag ratio, and we chose to use the MB 25, 35, 15 section on the inner part of the blade in order to stop any fracture as we get closer to the root. Another part of our design was designed to have a hexagonal hub, mainly because there was no chance of slippage, and this would give us the best chance of achieving a high power when the turbine was slowed down. It's actually now important to consider the structural analysis of the blade. We mainly consider the effect of centrifugal force due to rotation, and also the lift and drag forces that are being produced by the blade. To ease the calculations, and due to its relative magnitude compared to the other forces, we neglect shear stress in this case. Two ways we can solve to find the stress. One is through beam theory and idealization, such as in the aircraft vibrations lab, or we could also use finite element analysis, which is what was attempted in this case. We used the optimized blade from Q-blade, and converting this into an STL and putting this into ANSYS CFX, we were able to create a mesh of the blade and then run a CFD simulation in order to predict the relative stresses along the blade at 12 meters per second, running at our predicted TSR of 6. We further optimised the blade in order that the braking stress occurred at 3,500 RPM, giving us a safety factor of 20% over the initially predicted value of RPM. And we can see that this analysis was very accurate, because when the blade did exceed 3,500 RPM at our 12 meters per second test, the blade did break 0.08 meters from the hub, so roughly the same as what the finite element analysis predicted.
Upon the completion of the design process, the next stage is to actually manufacture the wind turbine. The nose cone and the wind turbine blades are manufactured by a process called fusion deposition modeling, which uses a rapid prototyping machine. A STL file from CAD is imported into a software which mathematically slices the components, and then the material is deposited in layers, hence a 3D model was created. The material used is ABS plastic, which means the components are light and also rigid. The next step is to actually create the aluminium hub. This is made manually in the workshop by processes such as turning, which produces spherical or circular components, and milling, which produces prismatic or irregular components, and also finally broaching, which actually allows us to produce the key-ring. Also, it should be noted that the aluminium hub has a one threaded hole to allow non-permanent and efficient assembly with the hub and the nose cone. So once all these parts have been manufactured, the wind turbine is assembled, and it should also be noted that the dovetails are limited to being 20 centimeters long, so they're glued together to actually create blades, and then the whole assembly is sanded to ensure a smooth surface finish. And then, well, the wind turbine is ready to be tested.
Our wind turbine is tested in the Honda wind tunnel under 6, 8, 10 and 12 meters per second. As you can see in the graph, we attained the maximum CP at 0.267 when the wind turbine is running under 6 meters per second and giving out 17.59 watts as its maximum power output. And at the same time, the wind turbine is running at TSR of 7, which is a little bit higher than our designed TSR at 6. Fortunately, the wind turbine broke at 12 meters per second, which Sergio will explain on it later on. We are also able to note some unusual spikes at around 1800 RPM, which is the resonance of the frame and causes instability to the power output of the turbine.
In our structural analysis calculations, we considered loads sustained by the structure at 3000 RPM, and we took a safety margin of 500 RPM. In the wind tunnel testing, it actually failed exactly at 3500 RPM. We looked at the structure under an optical microscope with a magnification factor of 114, and we can clearly see on the fracture face an amorphous state which is seen as translucent, and a region where crazing occurred, which can be seen as white. Whilst we were sanding the structure, we could observe a section which might cause problems, and this was actually the region where the fracture occurred. It initiated at the trailing edge and then propagated through the ABS material until it reached the dovetail joints, at which point it split the joint apart, and the joint failed through an adhesive failure.
There are a number of improvements we could make to our design. The first would be to thicken the blade at the part which broke. This would be in an attempt to increase the maximum load which the blades could withstand. One of the design criteria was for the turbine to not exceed 3000 RPM. Our turbine did exceed this. We exceeded the maximum frequency of 3000 RPM at 12 meters per second. And so another improvement we would need to work on would be to increase the drag of the blades so this didn't happen again. We found that both the hub size and the nose cone size were a little bit larger than needed. This would mean that one more improvement we could make would be to reduce these in size, to reduce the weight of the turbine, and this would increase our merit function. What our wind turbine really showed was that the aerodynamic performance of it had great potential, and if we were to repeat this project, we would be able to make the turbine a lot lighter with the same properties aerodynamically. This would produce a much better wind turbine, and I believe that this is a great foundation to work off.
We started with a design we really loved, but to build it, to implement it, we had to look beyond what we thought we were capable of. It took all of our knowledge, all of our understanding, all of our learning to realise something so simple, so clear, so truly extraordinary.
About the stars and how you'd make it up there one day. I would hum and whistle through, and you would try to get the tune, but you'd never really heard it anyway. You told me about the only one who'd ever really showed you something you had truly never seen before. And up until that very moment, nothing else had seemed important, everyone a disappointment. So